Since Zoom conspired against us this morning, here is a recreation of this morning's class. Um, again, we're continuing our discussion of sig figs, and as we were saying last week, right, for the most part, sig figs are pretty straightforward, right? I'm trying to only write the numbers I actually measured. And so for the most part, for the numbers 1 through 9, if I see them, they're significant because there's no point in writing a 7 unless I know it's a 7. Right? The only number that is sometimes a problem is 0 because of one particular type of 0. And so I can have what are known as trailing zeros. And if these trailing zeros are after the decimal point, again, there's no reason to write them if I didn't measure them, right? And so, you know, here's a 0, right? Must have measured it. Because if I take that 0 away, it's still the same magnitude number, right? And so, you know, unless I just feel the need to add as many zeros at the end of a number as I want, right? There's no point in writing any of these 4 zeros unless I actually measured them. And so trailing zeros after the decimal point are always significant because you would not write them unless you knew them, right? Leading zeros are also actually known, but because there's an infinite number of them, they're not viewed as ever being significant. And what I mean by that is you can always put a 0 out in front of a number. It doesn't change anything, right? 1, 2, 3 is a number. 0, 1, 2, 3 is the exact same magnitude number. Because I know, right, 123 has 0 thousands. It has 0 10 thousands. It has 0 10 millions. And so because I could put an infinite number of zeros out front, right, they're simply not viewed as significant, even though they are known numbers. They are, in fact, zeros, right? Zeros in the middle, right, they're significant because, again, there's no reason that you wouldn't know that 0. The one set of zeros that are problematic are trailing zeros if they fall before the decimal point at the end of a number, like these two numbers, 1, 2, 3, 0, right? And 1, 2, 3, 4, 0, 0, because this 0 serves one purpose and one purpose only. It tells me the number is not 123, right? If I take that 0 away, I don't know that there's actually another digit before the decimal point. And so these zeros are referred to as place marker zeros. They have to be there to tell me where the decimal point is, but they have to be there whether I measured them or not. And so I can't really know whether they were measured or not if I see that number, right? And so those zeros, trailing zeros before the decimal point, are the only ones that present a real challenge, right? So for example, if I told you I weighed 100, 200 pounds, right? I don't know how many sig figs that is because it could be any one of 3 different things, right? If I actually measured my weight to the nearest half pound, right, that's 3 sig figs, right? I'm 200 plus or minus half a pound. On the other hand, maybe I didn't measure that last 0, right? I measured to the nearest 10 pounds, which is plus or minus 5 pounds. Now I only have 2 significant figures. And in fact, if I did a really coarse measurement, and I only measured myself to the nearest 100 pounds, right, that's plus or minus 50 pounds, I really only then have 1 sig fig because I actually didn't measure either one of those zeros. All right, and so if I write 200 as a measurement by itself, it does not give me any indication of how many actual sig figs are in the number because the zeros are really only trying to tell me where the decimal point is, right? The solution to this problem is scientific notation, right? And in some sense, this is the only reason scientific notation exists, right? Some people sometimes say, you know, it exists as a shortcut for writing big or small numbers. And that can be true if it's a really, really big number with a lot of zeros or it's a really, really small number with a lot of decimal points. But a lot of times it's actually longer to write the number that way. The real power of scientific notation is that it does not require me to write any numbers that are not significant, right? Scientific notation always has the same format. It is a non-zero number followed by a decimal point, followed by every other significant measured number. And then it has a powers of 10, which is actually just telling me where the decimal point is. And so by putting decimal position as a separate part of the number, right, I no longer need place marker zeros. And the place marker zeros were my only real significant figure challenge, right? So if I want to write 200 pounds in scientific notation, right, I can write it unambiguously with respect to the number of sig figs, right? I put the decimal point after the first non-zero number, which is the 2. If that was the only measured number, right, here's my place markers, right? Times 10 to the second is telling me there are 2 0 place markers in that number. But I don't need to write them because the times 10 to the second tells me where the decimal point is. And so all I'm left with is the one and only significant figure. On the other hand, if I had actually measured to the 10th place, right, so that I have 2 significant figures, I can unambiguously write that in scientific notation. I put, again, the decimal point after the first non-zero number, and I add as many significant figures I have, which in this case is the 1 0, right? And again, the times 10 to the second tells me where the decimal position is. And so this is now unambiguously 2 sig figs. In scientific notation, every digit you write is significant because there's never a reason to write a non-significant digit, right? I can do the same with decimals, right? In this case, I'm now moving the decimal point to the right instead of the left. But again, I move the decimal point to right after the first non-zero number, which in this case is a 3. The format is exactly the same. It's one and only one digit before the decimal point and the rest of the significant digits after the decimal point, right? And then my times 10 to the number tells me where the decimal point is. In this case, because I moved 1, 2, 3, 4 places to the right, it's 10 to the minus 4, right? In this case, with the 200, because I had moved 2 places to the left, it's times 10 to the plus 2, right? And so my powers of 10s are really just place markers to tell me where to put the decimal point. And in scientific notation, the key is every digit you see is significant. So there's no place marker zeros here. If I wrote these, it's because I measured them. And so that's 4 sig figs, right? This is 5 sig figs, right? And this is really just telling me where the decimal point is. Okay. And so again, you know, here's a whole lot of zeros. It becomes clearer in scientific notation what's significant and what's not. I move my decimal point to right after the first non-significant digit, right? My trailing zeros always significant. That is 4 significant digits. Right. Preceding zeros are never significant. Trailing zeros after the decimal point are always significant, right? The only time trailing zeros are not significant is if they are place markers. And so scientific notation gets rid of the place markers. Right. There is one other way to sort of move the decimal point around, and that is by using prefixes with my units, right? The SI unit of length is meters. Meters about this big, right? Now, if I'm measuring things like human beings, meters is a good unit of length, right? I'm just a little over 6 feet tall. That's a little less than 2 meters, right? Meters make sense for my height, right? On the other hand, a planet is much bigger than me, right? I could still measure it in meters, but I need a whole lot of meters, right? On the other hand, if I measured something like a human cell, or the thickness of a human hair, it is way less than a meter. And so it would be a tiny, tiny fraction of a meter. And so you can do that with zeros, right? If you want a bigger number of meters, take 10,000 of them, right? If you want a tiny fraction of a meter, take 0.000001 meters, right? On the other hand, I could also just make my unit of measure bigger or smaller. And that's what these prefixes do. They're really just powers of 10. So in a sense, again, they're moving the decimal point around. But what they're trying to do is to create a unit of measurement that's appropriate to the size of the thing I'm trying to measure, right? So a megameter, big M, little m, right? M for mega, little m for meter, is 10 to the 6 meters. It's 1,000,000 meters, right? I would not measure my height in megameters. I'm not that tall, right? But I might measure the distance between the Earth and the Moon in megameters because it's a more reasonable unit of length. I might measure the size of a planet in megameters, although it has to be a fairly big planet, right? Kilometers is 1,000 meters, right? If you're in or from a metric using country, right? The most frequent unit of distance on a map is a kilometer, right? It's 1,000 meters. Why? That is a reasonable city-sized distance, right? And on the small end, you could use something like a micrometer for the thickness of a human hair. It's 1,000,000th, 10 to the minus 6, of a meter, right? And so these prefixes really just move the decimal points around, and they're just trying to create a unit of measure so that I don't need thousands and thousands of meters. I just have a few kilometers. I don't need millions and millions of liters. I just need a few megaliters, right? In the end, all of these things are really just trying to tell me accuracy, right? My sig figs, right, are just telling me what digits I actually measured, right? The scientific notation adds nothing to this other than giving me an unambiguous way of expressing only the measured digits. If I then combine that accuracy with a unit, I now have a piece of data, right? Because the unit tells me the context of the measurement. Was it a length? Was it a weight? Was it a volume? The number, with the appropriate number of sig figs, right, tells me the magnitude of that measurement. And because I'm using the sig figs, it also tells me how accurate that measurement was. And so really, to create a good piece of data, I want both things. I want as specific a unit as possible, right? Because the more specific it is, the clearer it is what I measured, right? Meters is great. Meters of height is better. Meters of Joe's height is even more specific because I now know exactly what to measure if I want to repeat your measurement, right? And the number of sig figs tells me how accurate the measurement was, right? And again, if I've got a big number of units, I can combine them into a smaller number of bigger units, right? And so if I measured a planet, you know, and the circumference was 167,000 meters, I could write it as 167,000 meters, 535, 167,535. It's 6 sig figs, right? It's still 6 sig figs if I write it in scientific notation. On the other hand, because it's a whole lot of meters, I could also use a bigger unit of length, which is a kilometer, right? Kilo means 10 to the third. And so essentially it's just moving the decimal point 3 decimal positions to the left, right? And if I wanted to, I could have gone even bigger all the way to a megameter by moving it 6 decimal positions to the left, right? Now, that brings us to what we really ultimately want to do with our data, right? I mean, you know, there's times I just want to measure something, right? They ask me on my driver's license how tall I am. I need to measure my height, right? On the other hand, right, in science, I'm usually doing the measurement because it's a piece of information that ties to some other piece of information, right? And so I don't usually just measure something and report it. I measure something and do something with it, right? And so sometimes that thing I do to it is to change it into some other unit of measure, right? And there's what I like to think of as two different reasons I would do this. One is a scientific reason, right? I measured weight and I want volume. Those are two different physical quantities, right, that are related in a scientific way, and so I can do that conversion. That is a meaningful scientific conversion, right? If you want a somewhat less scientific, but, you know, a common conversion, I need to travel 200 miles to visit my mother, right? How long will it take me to get there? I'm now turning distance into time, right? And of course, all depends on how fast I'm going, right? That is a meaningful conversion because it is distance, which is one unit of measure, one fundamental unit of measure, which I turned into time, which is a different fundamental unit of measure, okay? Ultimately, that's what we want to do. And starting on Wednesday, that's what we'll do, right? There's also what I like to think of as editorial changes, right? Which is I've got a unit of distance. I want a different unit of distance. Why? Purely editorial preference, right? I've got distance in meters. I'm in the United States, pretty much the last nation on earth that uses miles, right? I need to convert my meters to miles to talk to my audience. That is an editorial change. It's still just a distance. I didn't do anything scientific to it. I didn't convert it to anything different. I just changed the reporting unit, right? But either way, it's fundamentally a unit conversion problem. And so everything we do in this class is fundamentally a unit conversion problem, whether it's editorial, like what I'm doing here, or whether it's scientific, which is what we'll be doing for most of the course, okay? And conversion, right, really depends on equivalence, right? We could talk about Joe's, but, you know, arbitrary unit of measure, because every scientist wants a unit of measurement named after them. A more normal and actually correct conversion is feet to meters, right? 1 foot, one measured foot is 0.3048 meters. This is equivalence, right? If I have something that is 1 foot long, it is also 0.3048 meters long, right? And the reason that's important is because when I have equivalence, right, I have essentially equality, at least in magnitude. And so I can do what's known as dimensional analysis, also sometimes called factor label method, right, which uses conversion factors to make either editorial changes or scientific changes. But it all relies on the existence of equality, because what I'm really doing is changing the units. I don't want to change the magnitude, right? In common parlance, this happens all the time. It's one of my pet peeves, by the way. So, you know, sometime this week, you know, you can use it on me, right? You'll say, Dr. Joe, do I multiply by 2? And I will grind my teeth and say, we never multiply by 2, right? Because multiplying by 2 means doubling what you have. Dividing by 2 means cutting something in half. We really almost never do that. What we do, right, is to actually change the units without changing the magnitude, because I'm always looking for equivalence. I've got feet, I want meters. I'm not going to change the length, I'm just going to change the unit. And the way I do that is to multiply by 1. Because 1 is the multiplicative identity. If you multiply anything by 1, it does not change its magnitude. 1 times me is still me. 1 times my height is still my height. But if I'm clever about choosing my 1, I can change the units without changing the magnitude, right? And so if you want a really simple example, 1 foot equals 12 inches, right? This is so simple. If I asked you to do the problem I'm going to ask you in a minute, you would just do it. You wouldn't even think about it. Because it's so simple and you're so familiar with it, you do it without thinking about it. When it's a chemical unit, it suddenly seems less familiar and maybe scary. And so I only present this example to make you conscious of what you already know how to do, because it also means you already know how to do the chemical conversion, right? I want to use my 1 as a means of changing units and not magnitude, right? And so here's my height in inches, and I want my height in feet. And I know what you're thinking, divide by 12. And you're both right and wrong, right? If you divide me by 12, you are cutting me into 12 equal pieces. That is probably not what you want to do, at least not yet. We'll wait till the midterm, right? What I really have here is something I know and something I want to know. And in the context of my life is units, 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 and I will say that a lot, right? And my life is units, units, units. That thing I know is a unit, and that thing I want to know is also a unit. And all I'm really looking for, whether it's editorial or chemical, is some pathway which takes the thing I know, right, and turns it into the thing I want to know. In this particular case, the thing I know is my height in inches, 73 to be exact. And I want my height in feet, right? There's a unit I'm starting with that I don't want for whatever reason. And there's a unit I do want, feet, for whatever reason. In this case, since they're both units of length, it is strictly editorial. I am no taller or shorter, right, when measured in inches or feet. I've learned nothing new about myself if I go from inches to feet. If I went from inches to pounds, for example, I would have learned something new about myself, right? That's a more scientific conversion. Here, strictly editorial. And as I like to say, right, all of my conversions are half obvious, right? Because they really start with one fundamental rule, right? I don't want what I have. I've got inches, I don't want it. If I did want it, there's nothing for me to do, right? I should put this question on the midterm, see how many people it confuses. I am 73 inches tall. How many inches tall am I, right? If I wanted inches, there's nothing to do. The only reason there's something to do here is because I don't want inches, right? I do want feet, right? And that's okay. Whoops. I just need to get rid of inches and to create feet, right? And so the thing I want to do, as I like to say, is always half obvious. I need to get rid of inches, right? What I can turn it into is not always obvious. It kind of depends on what I know about inches, right? But obviously, I don't want inches, so I need to get rid of it. So inches, which started up here, has to go down here to cancel. And I want to turn it into something new, right? Ideally, I want to turn it into feet, right? So the one conversion, which is always 100% obvious, is the one-step conversion, if you can find it. You know, there's a Google engine out there. You can find almost anything. If you type in how many inches in a foot, it'll tell you, right? For some of our conversions, not so easy, because each conversion represents something scientific, and you can't always combine all of your scientific steps into one big step, right? But my shortest pathway from the thing I'm starting with, the thing I'm finishing with, is to take the unit I don't want, put it on the bottom and cancel it, and take the unit I want, put it on the top and create it, right? In this case, I do know, right, that 1 foot is equivalent to 12 inches. That is really two different conversion factors. If I divide both sides by 1 foot, I get 12 inches over 1 foot equals 1. If I divide both sides by 12 inches, I get 1 foot over 12 inches equals 1. Either way, it's a 1. If I multiply it by something, it does not change its value, right? In this case, I want inches in the denominator to cancel inches, feet in the numerator to create feet, right? And I now have my height in feet. It's actually 2 sig figs, which is something we'll talk much more about on Wednesday. But for now, my point is the conversion, right? I take the unit I have and don't want, and I get rid of it, and I create the unit that I don't have but do want, right? And again, this does not necessarily have to be a one-step process. If I stick to length for a minute, I don't necessarily have to go directly from inches to feet. Obviously, in this case, I know the conversion. But maybe I didn't. Maybe I know inches to millimeters, and I know millimeters to miles, and miles to yards, and yards to feet, right? No matter how many conversion factors that there are, there's always 2 things I can say about it. Each one of those conversion factors is just a fancy 1, right? It is the exact number of millimeters that equals the exact number of inches, right? And so as a magnitude, the millimeters over inches has a magnitude of 1, right? And so it does not change the magnitude, right? It does, however, change the units, because the second thing I can always say about this, each of these conversion factors, is they always do one thing and one thing only. They get rid of a unit and they create a unit, right? My first conversion factor here gets rid of inches and creates millimeters, right? I then have millimeters, right? Well, I didn't want millimeters, I still wanted feet, so you know what? I'm going to get rid of millimeters. So I put millimeters in the denominator, that gets rid of it. I went to miles. Is miles better than millimeters? I didn't want millimeters, so no loss, right? Then it went from miles to yards, and then yards to feet, right? I had a student once who referred to these as the railroad tracks. Don't ask me why. I was never 100% sure, right? But the unit I'm creating always goes on the other side of the tracks, right? And so inches was in the numerator, it went to the denominator, that got rid of inches. Millimeters went in the numerator, it got created, right? In the end, I got feet. And as I like to say, if you got the right unit, 95% of the time you got the right answer, even if you don't know why you use those 4 conversion factors, right? Because the units are really what's defining my information for me, right? And yes, that was too simple, because you could do that in your head, because it's something you're familiar with, right? One of the real problems in chemistry, but in almost any discipline, is there's a certain cognitive dissonance when you enter a field for the first time, because the terms are not familiar to you. It's made worse, by the way, if you hate chemistry or whatever that subject is. So you need to fake it, right? Pretend you love chemistry. It at least removes that one hurdle, right? But it's simply the lack of familiarity that makes chemistry seem harder than going from feet to inches. When I would like to maintain pretty much all we do computationally, 90% of the time, is convert feet to inches. It's just not feet anymore, and it's not inches anymore. It's grams of lead, right, going to moles of lead, or it's grams of lead going to grams of aluminum, right? They are now more chemical units, but I'm still doing the same basic thing, which is to always get rid of the unit I don't want and create the unit I do want, right? And so they will be more scientific, more chemical units in nature, but it's the same basic process we just used, right? Ask yourself what you know. And by that, I mean units, units, units. What is the unit you have? Right? What is the unit you want? If they're the same thing, you don't have a problem to solve, right? And so they're almost always not the same thing. And so now I need to change the unit I have into the one I want. That might require multiple conversion factors, and it's really largely a function of what relationships I do or don't know, right? But I just do it one step at a time, get rid of one unit, create a new one, always with an eye towards moving towards the unit I want, right? Here's a somewhat more chemical sounding unit. I have 32 milligrams of lead per milliliter of wastewater. I want that in pounds per gallon, right? It might be easier if I write it this way, right? As an actual fraction instead of writing it in line. I have a contamination, which is what this is really representing, of 32 milligrams of lead per milliliter of water. This, by the way, is a huge amount of contamination, right? And I want pounds of lead per gallon of water, right? We talked last week about the need to be specific with the units. This is helpful here, right? I could have written it just as milligrams. I mean, that's what it is. It's a mass. I weighed it. It was milligrams, right? But I wrote it as milligrams of lead because it is specifically referencing the mass of the lead. And in the end, I want pounds of lead. Right. That actually gives me some hint as to what I'm trying to do, because I'm not trying to turn milligrams into gallons, because milligrams refers to lead and gallons refers to water. And while I could convert milligrams into gallons, right, hard to convert lead into water, right? And so having the more complete unit gives me a clearer sense of what I want to do, right? Since it's hard to convert lead into water, and I'm not doing a chemical reaction here that would do such a fantastic thing, right? It only makes sense the lead stays lead and the water stays water. And so I'm trying to convert milligrams of lead into pounds of lead, and I'm trying to convert milliliters of water into gallons of water. Right? Here's a case where there is no single step path, because it's not immediately obvious, right, how many milligrams of lead per pound of lead, right? And I'd also have to do the conversion all at the same time, because I need to convert milligrams to pounds and milliliters to gallons. At the very least, it's 2 conversion factors, right? But again, I don't have to plan it out too far in advance. I just need to know what my first step is. And my first step is to get rid of a unit I don't want, right? And which, in this case, could be either the milligrams of lead or the milliliters of water. I don't want either one of them, right? And so I'll start with the milligrams of lead. I'm going to convert milligrams to something, right? Ideally, if I want to do it in one step, it would be pounds. And you know what? If I got Google, I can do it in one step. Go Google milligrams to pounds, and it will give you a conversion factor, right? I then want to convert milliliters to gallons. Again, I could Google it, right? So I got milliliters is initially in the denominator. I need to put it on the other side of the railroad tracks. So milliliters goes in the numerator, so it cancels. And the gallons I'm trying to create goes in the denominator. Right. And again, if you Google it, milliliters to gallons, it will tell you. Right. Right. On the other hand, I'm too lazy to Google, right? I actually know one English to metric conversion for everything. Don't ask me why. For volume, the English to metric conversion I always remember is liters to quarts. So if I'm doing a volume conversion, I always go from whatever I've got to either liters or quarts so I can cross over, right? And for mass, the thing I always know, don't ask me why, is grams per pound. And so no matter what the unit of mass is I have, I either go to grams or pounds so I can cross over. So for me, it ended up being 3 conversion factors. But again, it does not matter, 1 or 3, it takes me a little longer. Each one of those steps does the same thing. I've got milliliters of water. I want to get rid of it, so I put milliliters in the numerator. All right, a milliliter is 10 to the minus 3 liters, or said the other way, 1,000 milliliters is a liter, right? I shouldn't really have canceled the 1,000 also. So my milliliters cancels. I now have liters down here. I want gallons, not liters. So again, I'm going to cross over because the one thing I know is quarts per liter, right? And I also happen to know that there's 4 quarts in a gallon. And so it took me 3 conversions. You Googled it and did it in 1. You got done faster maybe, right? But the bottom line is, right, we both got to gallons, we're both right, right? I need to do the same thing in the numerator because again, I didn't want milligrams, I wanted pounds. Again, I always know that 1 conversion factor, which in this case is grams to pounds. So I needed to get to grams. So again, milligrams is up here. So it goes down here, so it cancels. 1 gram is 1,000 milligrams, right? And then again, I wanted pounds, so I need to get rid of grams. So here's my grams in the numerator. I put in the denominator and pounds in the numerator, and voila. If I punched all that into my calculator, I get 0.26697 pounds per gallon. And again, mostly foreshadowing Wednesday's talk, right? That should actually be 2 significant figures again. Right. And so I would really write it as 0.27 pounds per gallon. And in some sense, that is 90% of what we do in here, right? Ultimately, right, a lot of what we do is to combine pieces of information to create other pieces of information. That means we're using numbers to calculate things, right? As a result, right, if I'm going to have the right accuracy in the number I calculate, I need to know how the sig figs, right, track through the calculation. Right? Because again, if I do 10 measurements and turn them all into one other number, that number does not have infinite accuracy. My calculator told me that this number had 5 sig figs in it. It does not, right? And so we'll mostly talk about this on Wednesday. I will introduce it now, right? If I'm talking about sig figs in a calculation, there's actually 3 rules. One that applies to logarithms, so we won't talk about it now because we don't need any logarithms for a little while. But there's 2 main rules. There's one for multiplication and division, and there's one for addition and subtraction. Right? And because I'm trying hard not to lie to you any more than I need to, and certainly less than your high school chemistry teacher lied to you, right? These rules are really a shortcut for what I would really want to do, right? Because ultimately, again, it's an issue of how the measurement was taken and what its inherent accuracy is, right? And so if I measure something and it's 12 inches, well, that's certainly not going to work, right? What I'm really saying is the number is somewhere between 12 and a half. I mean, really 12.4999, because if it was 12 and a half, I'd round it up. And somewhere between 11 and a half and 12 and a half, right? Because a measured number is not an exact number, right? It's a range of values around that depending on my degree of accuracy, right? And if I measured something else and I got 9 inches, so let's say I'm measuring a rectangle here, right? Again, that 9 isn't exactly 9. It's somewhere between 9.5 and 8.5. Right? And so if I multiply those two numbers together, I get 108. But not exactly 108. Because really, right, since I don't know the exact number, right, it could be as high as 9.5 times 12.5. And it could be as small as 8.5 times 11.5. So really, this number, right, is in the middle of a range of numbers where I've got a maximum possible area for my rectangle and a minimum possible area for my rectangle. And that's why it doesn't make a lot of sense to speak about 108 as though it's an exact number, right? If you actually do the math, this is like a little bonus for those of you watching the video since we didn't get to do the math in class today. Right, 12.5 times 9.5 is 118.8. And 11.5 times 8.5 is 97.8. Right, so the actual area of this square is some number between 97.8 inches squared and 118.8 inches squared. So it makes no sense to speak of it as though it's 108 inches, because that's 3 sig figs. Clearly, those are not all significant. Right? In fact, I only have one significant figure in that number. And you can see it kind of if you look at the range, right? This is 100 inches squared, right? Excuse me, yeah. Which is in this range. Truly, 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 if I wanted to do all the hard number crunching every time, what I really want to specify is this as my entire range of values, right? Which is why I say my rules are a shortcut, right? They're a useful shortcut, but they're ignoring effectively the range to allow me to simply state a number of sig figs, right? And we'll talk on Wednesday about exactly how that works. Happy Monday.